To this on-demand presentation, which takes an application focus to help a user select the right laser diffraction particle size analyzer. Before we begin the presentation, let's meet today's speaker. Presenting today is Microtrac's own Dr. Philip Plants. Dr. Plants earned his PhD from Penn State University and has over 30 years particle science expertise. Now let's hand it over to Dr. Plants.
I want to thank everyone for joining us this morning. And I just want to mention that we've been innovators in light scattering since 1974. We have many patents in the area. We developed the very first dry powder sampler, which would allow dry particles to be measured by light scattering. We have complete organic solvent capability without it making any changes to the system. All that's really required is a change from the aqueous system to the organic solvent system. We use what is called a Fourier optical system, and this provides for the best resolution in calculations. And this I will discuss in a very short detail in just a couple of minutes. We also innovated using bent optics. Bent optics is merely redirecting the laser by a series of highly polished mirrors. This provides for a small footprint, lightweight, and actually provides quite a bit of stability to the optical system since it's a small footprint. We also use nothing but laser diodes, both in the blue region as well as in the infrared. Now, our 780 nanometer lasers are often called red lasers, but they are in fact infrared lasers. These laser diodes provide for a very, very long life, upwards of 20 to 25 years as far as we can tell. It also provides instant on and pointing stability. There's no neon warm-ups that you might find with helium neon gas lasers. Our detector design is based upon volume. All the calculations are designed on volume. We don't do any type of a conversion from area or number of conversions to volume. We have spherical and non-spherical models, and I'll go into a little bit about this. This is really demanded for the best possible calculations because the scattering from spherical particles and non-spherical particles, as I'll be able to show you, can be quite a bit different. Back before the world of Microsoft and Apple, we actually had PC applications where we actually had a color display in 1981 for all the data. And recently, since 2009, we've developed an integrated system of diffraction and imaging. This instrument is called the Part-An SI, and I'll show you an example of why that can be valuable. And we've had this instrument since 2009. The use and application of the instruments and the ranges and the particle size response, as Jason mentioned, we actually have three different instruments. One is the 3500, which has been around for several years. We have the blue wave instrument as well as the tri-blue. Now the S3500 uses three 780 nanometer lasers. It can measure from 20 nanometers up to 2800 microns. Its primary use is for particles above about 60 nanometers. We introduced the blue wave to take advantage of 405 nanometer lasers, which are well into the blue region, and it has one 780 nanometer laser, and this will measure the large particles and the small particles. Now the blue wave below a couple of microns has highly enhanced calculations, and this is to pull out the smaller particles using these two 405 nanometer blue lasers. Subsequent to the blue wave, we went further with our innovation and advancements and introduced the tri-blue instrument. Here we use three 405 nanometer lasers. Now, this will measure large and small particles, but you'll notice the limit on the size is around 704 microns. Now, generally, most applications are from just a few hundred microns on down. So the limitation here is probably not much of an issue. If it's necessary to measure above that size, then the blue wave would probably be a better choice. But the tri-blue has advanced calculations. We took the calculations from the blue wave and spread them across the entire range because we're using a single wavelength. And this goes back to our shift invariant concepts, which requires the Fourier optical system. So with these advanced calculations, and I'll show you some data on this that on each one of these different situations. So one of the questions is, why use blue lasers? Well, blue lasers provide for full collimation rather than trying to use LEDs or bandpass filters. It provides an extremely high intensity from the small molecules. Now, if you'll notice, I've got a drawing here showing the differences in how light is scattered from smaller objects. And as we get down here into the 405 nanometer range, you can see the scattering from the smaller particles is much greater than what you'll find out here. And this doesn't take it all the way up to 780 nanometers, because this is the visible spectrum. But you can see that the scattering from the smaller particles is much greater. In fact, the scattering from the blue lasers compared to the near-infrared or red lasers is on the order of at least 10 times better scattering from those small particles. But this is the reason why our sky is blue. Those small molecules and small dust particles in the atmosphere scatter the light very well compared to the reds that are in the visible spectrum. Thus, during the daylight, the high scattering from the small particles preferentially scattered the blue region of the sunlight very strongly compared to the other colors. Thus, the sky is blue as we wake up in the mornings and throughout the evening, until we start to get the sunset. Then the angle of the sun on the atmosphere starts to change, and then as a result, the reds and the yellows and the pretty greens start to come through during the sunset. Now, the whole idea is that using the blue lasers provides the best angular measurements for calculations from the fingerprint that's developed from the light scattering concepts. And this is much better than using LEDs or filters. These would be bandpass filters for the small particles. Now, every one of the light scattering instruments that's ever been designed has three basic components. One is an optical system, one is an electronic system, and the other is a mathematical system. The optical system allows us to have the light interact with the particles. Obviously, that's the very first step. That has to happen. Then that light that is scattered is captured by a lens system. And then we move into the electronic system, and here we have a detector system that is logarithmic in design. We use a logarithmic detector array because of the theories involved with light scattering really demand that. We could use what's called a linear array where all the segments are all the same size, but there are some real issues with trying to do that. So once we have this light being detected, then the light is converted into electrical signals, voltages, and currents. These electrical signals are captured by the instrument, and this provides the actual fingerprint for that material. The next step is in the calculations, and these are deconvolution mathematics, and there are other ways of doing calculations, but we perform the calculations on the signal pattern. And as part of those calculations, we use calculations, and for irregular shaped particles, we have proprietary calculations for that area. And I'll explain to you why we have the two separate calculations, one for spherical particles and one for non-spherical particles. Years ago, we had an instrument called a small particle analyzer. It used one laser and several different bandpass filters, and we have patents dating back to 1976. Those patents ran out in the late 80s, early 90s, but we had already embarked on a new concept of trying to get away from using different filters and matching entirely different optical concepts. There could be some real issues with changes in those filters, which forced us to decide to find new concepts in light scattering. But by the time we get done with all the mathematics, out pops the particle size report. Now, the basic scattering concept, I'm sure many of you are familiar with this, but for those that are not familiar with it, just let me explain the basic concept here. We have a laser beam, and that's pointed down the optical axis, and this laser beam interacts with particles, both the small ones and the large ones. The larger particles scatter the light at a more narrow angle, but at a higher intensity than the small particles. Small particles scatter light at wider angles than the coarse particles. Now, the light then is captured by a Fourier lens, and that light is then focused onto a logarithmic detector. And you'll notice the sizes increase in the detector segments increase in size as we go out to wider and wider angles. And that's to take into account the lower intensity from which the small particles scatter the light. So this is the basic concept of diffraction instruments. I mentioned to you about the Fourier lens, and the whole concept of using a Fourier lens is to more or less substitute for using a mathematical Fourier transform, and as a result we get the same effect. Now, the whole concept that we've been using Fourier lenses since 1974. Now, let's take a look at the Fourier concept. The laser interacts with the particles, and this is the very first step in making our particle size measurements. The incident angle is the same for all the particles. Now, I'm assuming that this particle is not tumbling. That really is not the case. But let's assume that this particle maintains its orientation as it passes through the cell and it interacts with the laser. Now, with the laser interacting with the surface of the particles, regardless of where the particle is in the cell and where it interacts with the laser is incident on this particle at the same angle. As a result, the diffraction angle is identical for the particle regardless of its location in the cell. Now, using a Fourier lens, that light is captured and it's focused onto this location. And it will be at this location regardless of the location of the particle in the cell. Now, this provides for very high resolution, and it's the best use of using lasers, and that's the whole purpose of lasers, is to give high resolution and remove broadening of light scattering patterns. Let's take a look at what's called the reverse Fourier optical system. Here we have a lens, and this is a beam expanding lens, and this is normal. There's nothing magic here. But the laser then passes through a lens. Now, as this laser passes through the lens is trying to focus the light onto a particular location. But as the light is exiting from the lens, it will interact with the particle, and it will scatter the light and locate the scattering point over here. Now, when this particle is passing through the cell and interacting with the laser beam then is at a different angle as a result of using this lens. And as a result, as it interacts with the surface of the particles, it does not focus the light on the same location on the detector system. So immediately there is a broadening of this distribution. This can lead to over-reporting of finds. It can lead to extraneous report of coarser particles. It really depends on the size and the orientation of the particle, how that will play out. So the big difference is the starting point for calculations is the fingerprint, is the pattern of scattered light. With the Fourier optical system, it's very well defined. With the reverse Fourier, there are some questions about how this has to be dealt with. Now, one of the things that has always been desired since really the 70s, and we introduced the original Micrtotrac back in '74, was to extend the range of that original instrument, which started around 2 microns, and there was always a desire to get into the submicron region. So one of the ways that we could do this just using lasers rather than bandpass filters. If we have a starting point for the laser, and again, this is the optical axis pointing right at the detector system. Now, we can have the laser interact with these particles, but with our single detector and lens system sitting out here, we can only capture light over this particular angle. Now, this would represent the coarser particles, but we're losing all the information that we need to view the finer particles. Now, one way of approaching this is to relocate the laser and put it in different positions. And as I rotate the position of the laser, I'm actually swinging at the same time I'm swinging the light scattering pattern onto the detector system. And in this location, we're capturing some we're starting to look into the smaller particles. But as I continue to rotate the location of the laser beam, now I can see the widest angle scatters. And this allows me to see the coarse particles, the smaller particles, and also the finest particles just by rotating the laser from this location out to this location. Well, this is a nice concept and for detector lens assembly and one laser, but it does have some issues with how would one move that laser, and that means you would need motors and gears and things of that nature. Problem is with that, gears and motors tend to wear, and then alignment becomes an issue and stability of the system. So we had looked at using a single laser, illuminating the particles, but the first thought was to have a series of detectors that would ring the entire system out to 163 degrees. That's an awful lot of detectors. But as well, we would have a series of lenses to focus the light. And a multitude of lenses, since this is an optical system, presents certain issues. Just because of having so many lenses, if any one had to be cleaned, then it would all have to be cleaned. So from a customer point of view and maintenance, this is not a good idea. In addition, from a manufacturing standpoint, this would be a very expensive approach to manufacturing, time-consuming, many parts, and would increase the price of the instrument. So this concept was abandoned for what we call the tri-laser system. And over in this area here, we have a very highly reflecting mirror, and eventually the laser interacts with the particles, and the light scattering ensues. The light is collected over an angular distribution of I'm saying 0 degrees here, but it's more in the order of 0.02 degrees out to 60 degrees. This allows us to capture the information for the coarser particles. Now, the next step in this is to illuminate the particles using a 405 nanometer laser at a different angle. So in effect, I'm starting to swing that laser, but without actually moving it, because the lasers are all in place and are not moved. So at this point, we're collecting more light from 60 out to 80 degrees, and we're starting to include the fine particles that are involved in the particle size distribution. Now, the third part in the tri-laser system, we have the third laser, and again, the incident angle on these particles is now providing for a much wider range of scattering phenomena. And as a result, we can now collect light from 80 degrees out to 165 degrees. We combine this in the software, and obviously the software understands what detectors and lenses are being used at any given time. And we combine this into a total range of 0.02 to 165 degrees in the blue wave instrument. So this is the basic concept of the tri-laser system. We're swinging lasers into different positions, providing different incident angles without moving the lasers and without high complexity to the optical system. Now, one of the things that Micrtotrac introduced a number of years ago was the concept of making calculations on spherical particles and particles that are not spherical. Now, one of the things that this allows us to do because of these calculations is to make the refractive index selection very easy. There's no guessing, there's no playing with different refractive indices or anything of that nature to achieve a presupposed particle size distribution. As a result, part of this has to do with Mie scattering and what we call modified Mie calculations. Now, down here in the lower left corner, I'm showing the light scattering. This normalized flux, this is just a term for basically for intensity of light. And this area right here in my curve is the particle size information. Down here at the x-axis, I'm showing the different detector segments. Many of these are left off just so that I could blow up this graph. And if we look at these particles, and this darker color here is the fingerprint that you would find for a 6-micron particle that's spherical. And we notice that all of a sudden this particle size peak develops a secondary peak out here. Now this is a refractive component, and this is extra information that the algorithms will use to do calculations unless it's taken into account. For pure spherical particles like glass beads or a crystal ball, you would find this type of phenomenon occurring. This occurs particularly, these strong resonance areas particularly occur below about 20, 30, 40 microns, somewhere in that region. Once you get up to the larger sizes, these are reduced tremendously. But this has to be taken into account with spherical particles, because if it's not, it will show up as a secondary peak because the calculations will just run through that. So when we're talking about spherical particles, we are talking about true smooth spheres, and then you would pull in the spherical modeling, the spherical calculations to manage that whole situation. Now, up here, if we look at these photographs, this is the diffraction pattern that you would find from a spherical particle, and you'll notice that there's a series of light rings, dark rings, light rings, dark rings, etc., and that goes off into infinity. But this is the basic pattern, and we would have to, we must do calculations to account for how this pattern develops, as well as any refractive component. But in general, over approximately 95% of all materials that are manufactured in the world or measured in the world are not perfect spheres. And by the way, me studied perfect spheres, so me calculations are designed to deal with spherical particles. But as we start to change the shape of the particle from something that's spherical, then what we wind up with, if we look at something that's a hexagon, we develop a pattern like this. But if we go further with amorphous shaped particles that are not spheres, we actually get something that looks like this. So there's such a grand difference between a spherical particle and a regular shaped particle. As I mentioned a number of years ago, our research people embarked on looking at how can we actually handle this very effectively. The whole idea here is that these irregularly shaped particles with the refractive component and the resonances are tremendously reduced for particles that are transparent but also are not spherical in shape. So if we were to stay with the basic concept of using Mies scattering rather than realizing that irregular shaped particles actually have a different scattering phenomenon, then we would have to take this spherical calculation and somehow find a way to make it identical to this type of theory. So when we're asking for irregularly shaped particles, then this is the type of thing that we're dealing with. This provides the best starting point for the calculations going from our fingerprint of the signal pattern to the particle size. Now, in Micrtotrac instruments, materials that are considered opaque, and we're showing this down here, opaque particles, meaning black or dark blue or something like that, they tend to absorb an awful lot of light. This is the pattern here. And I just do want to mention that we use Mies scattering or modified Mies scattering across the entire range of the instrument. We do not use any Fraunhofer calculations because there are errors in that, even in some of the larger particle sizes. So this is why we have spherical particles and why we have calculations for irregularly shaped particles. Now, one of the applications, I've got a few applications I want to talk to you about, and there is a point behind each one of these. One of the applications is measuring chocolate. And chocolate is a complex food, believe it or not. But the flavor profile of chocolate includes a lot of volatile, non-volatile compounds, the smoothness, the texture, the flavor, a number of things. But one of the things that is important, that throughout the process of starting back here with the nibs and getting at the liquor particles. Now, cocoa liquor is the important aspect here. This is where all the chocolate really emanates. But you'll notice that the sizes are changing as we go through the whole process, and then we finally get down to the final products, and various particle sizes are as a result. Now, I'm not going to go through this table, but this webinar will be available on our website probably within a couple of weeks, and you can review this as well. But it does show certain aspects of chocolate manufacture. Now, I mentioned the chocolate liquor, and that is a very important aspect to manufacturing the actual chocolate. Now, these are liquors from various regional places around the world, and it's interesting to note that different cocoa beans give a final liquor that has a different size. Now, measuring the size of these liquors can be very important, because if the ultimate goal of the chocolate manufacturer is to have a particle size distribution, such as shown by this blue line, well, if he gets the cocoa beans from the location that will provide a liquor of this size, everything is well and good. But he may need to get product from other regions where the liquor has a different particle size distribution and contains extra coarse particles. Well, under these conditions, if he wants to achieve this particular distribution, he's going to have to mill this product. So knowing the particle size and monitoring the particle size throughout that monitoring process can allow efficient use of energy and to achieve the particle size distribution that's desired for the liquor. The other aspect of making measurements on chocolates and various chocolate products is that it's typically necessary to use an organic solvent or some type of fluid that will not dissolve sugars or other soluble compounds. Over here, this is a liquor, and it is using isopar G. Isopar G is an isoparaffin. It has a molecular weight somewhere around 10, 11,000, somewhere in that range. It's not a really pure compound, but it can be used, and it's very, very useful when you have measurements to be made for something that's very water soluble, such as sugar or salt, other compounds. And it is very good at not dissolving any of those particles. But the liquor here, when the first measurement is made, there's no ultrasonic treatment applied to it, but there's a lot of agglomeration throughout this area. So when we treat it with some ultrasonic energy, we find that the particle size shifts over here to this red line over here. And this is the true particle size distribution based upon having a well-dispersed system. Now, in many laboratories, the use of isopar G may not be allowed because of various other operations going on. Isopar G is a very safe, very low flammable, low ignition point solvent. But in food laboratories, that may not be desirable. So another choice, rather than using isopar G, is to use a material called niobe oil. Now, this is a food-grade oil. It is a gross substance, which means that it's generally regarded as safe according to the FDA. Now, niobe oil can be used, and you will achieve virtually the same result as using isopar G. Nice thing about niobe oil is that if it is being used, it can be disposed of very easily. If the material is being run in the niobe oil can be consumed, this can actually be used as a feedstock, or it can be recycled very, very easily, or potentially used in other areas in manufacturing. So it is possible to use various different solvents, some slightly higher viscosity fluids. We generally recommend not greater than 5 centipoise, but I know we can actually go higher than that. So this is showing two different niobe oils One is 1053 and the other one is M5. By the way, if you have any questions about these things and you want some information on how to obtain some of these compounds, if you will, just let me know and I'll make sure that you get the information. So we can use lots of different fluids, and the different organic compounds include all organic solvents. The system is designed for dealing with them because of the glass. The system is glass, Teflon, stainless steel, and solvent-resistant fluoropolymer O-rings. Second application has to do with the material called elastonite. And again, we're still dealing with the S3500, and this has 3 750 lasers. The major sources of this are from China and India, and elastonite can be used to substitute for other materials in various ceramics to promote strength and thermal dimensional stability. Now, measuring this on the Micrtotrac S3500, we obtain the following results, and I can't go through all this data here. If you're a Micrtotrac user, please visit one of our courses or anything else. Just call me and I'll be glad, or email me and I'll be glad to help explain the rest of this data. But let's go down to the graph here, and we can see that the graph, and this is a percent passing and also percent channel data. But looking at the percent channel data, we get a particle size distribution. And we can see that the particles range from somewhere around a micron up to a few hundred microns. But we really don't know much about this material as far as its total particle characterization is concerned. We do know it's a very broad distribution, and we do know there are coarse particles and fine particles. But if this distribution were to change, it would be a question, why is it changing? So the first thing one would do is hop over and take a look at this on a microscope and say, holy cow, we've got some very, very long particles that may have now been broken up that's caused that particle size distribution from the Micrtotrac to change. Well, there's a lot of information sitting in this microscope slide, but it's difficult to get size and shape information from a microscope. Even an automated microscope would have a difficult time dealing with this situation. So what we did, and since we have the Part An SI, which means suspension instrument, the SI is patched directly in series with the S3500, so we can get the S3500 data at the same time we're grabbing the image analysis. And the image analysis, I'm just showing you a couple of screens here. There's much more information that can be gained. But this shows some of the photographs of the from the SI as the image analysis is being taken simultaneously with the S3500 data. And we can see there are lots of needles. Now, I can't show you all the particles because there's on the order around 600,000 particles that have been measured throughout this measurement. So we're getting a really, really good look at the shape information. Now, what we did, and there are other graphs that can be used, but I put this in a scattergram for you. And we're looking at the aspect ratio. Aspect ratio is defined as the width divided by the length. So the smaller values, the lower values for the aspect ratio means that we have a small width to a very big long length. Now over here I have a plot of the length, and this is showing the micron sizes here, and we can see that the length of these particles goes out to 300 or 400 microns, just like the Micrtotrac was showing you. Now, the other thing I did was to put this together in a full scattergram, and this is showing the scattergram. Now we have the aspect ratio information, and we also have the length information plotted on the same graph. Now, supposing the manufacturer wants to have a very highly consistent product, or at least monitor and know how the length and the aspect ratio, which apparently is important to this material because of the shape of the particles, they may want to isolate on this particular area to make a consistent product. Then they may be able to do some processing to reduce the length of the particles and eliminate those particles, and also try to do some work over here to monitor the width of the particles. And this would give them a fairly consistent product that could be used in the ceramics. So this gives us the opportunity to mix diffraction information, and as well go much further with the characterization of the material by using image analysis simultaneously. Now let's move on to the blue wave. As I mentioned, the blue wave has enhanced calculations, and one of the things that the Micrtotrac is quite capable of doing is making measurements of black ink and dark colors. Now the customer in this case had asked us to make the measurements in ethylene glycol. Well, as we follow through our laboratory SOPs, well, one of the first things we do is test the material to find out if it's going to wet out and mix well with any particular suspending fluid. And what we find is that as we take this black ink and put it into ethylene glycol, the ink sticks to the pipette. It tends to float. There's some attempt for it to mix with the fluid, but this photograph doesn't show it, but these particles are actually trying to escape. They're actually starting to float towards the surface and trying to escape the ethylene glycol. That immediately told us trying to make this measurement ethylene glycol was not going to work. And if we were to put this into an instrument, it would cause it to get the optical system, at least the cell, to become dirty, and then it would have to be removed and cleaned and those types of things. So this is a valuable first step anytime you're going to be dealing with any type of an unknown. Well, this is the material. This is a premix, and instead of using ethylene glycol, Tony Weigel, our laboratory manager, put together a solution of isopropyl alcohol, and this is 99% isopropyl alcohol, and made it 1% in Tritenex 100. Merely by mixing the ink with this material, you'll see a lot of agglomerates, but this is not the final step in the preparation. But it does provide us with information that the sample is mixing well, and we just have to look at it a little bit more deeply. Well, with this microscopic photograph, we treated the sample for 45 seconds with an ultrasonic energy, and this is what's called a premix. And you can see there are larger particles still present in this sample, and but everything seems to be pretty well dispersed in general. But even during the first pass, taking this material and trying to make it smaller, the first pass through a mill, you can see that the particles have now started to get smaller. The length has started to decrease, and so this is starting to show the information that the customer was searching for. They were not able to achieve good particle size measurements with the procedures they were using. Now, what I'm showing here is that ink, and these are different times. This is before milling, and this is after milling, but prior to using ultrasonic probe to achieve complete dispersion. Over here, I have the graphs for 4 different samples, and this shows the data after the ultrasonic treatment. The 4 different samples is a premix, the first pass through the mill, 4-hour milling, and then 10-hour milling. Now it's kind of hard to distinguish what's happening here in this 2-dimensional graph. So what I did was use the Flex software and put the graph into a 3-dimensional mode, and now I can get a much better idea as to how these distributions are comparing. Over here, again, we have the samples having not been completely dispersed, but there is an indication that starting from the premix and going down to the first pass, and then the 4-hour milling and the 10-hour milling, there's an indication even here that fines are actually starting to be produced, which is what the manufacturer was hoping to see. But after we treat the sample with ultrasonic energy and get a full dispersion, we'll notice that the premix has a shoulder here, but as the milling continues, that shoulder tends to disappear, and then we're starting to see this peak develop up in this area here. But as we go further to the 4-hour milling, this shoulder that existed with the premix is now starting to almost disappear, and by the time we get to the 10-hour milling, it has disappeared, and the whole particle size distribution is now trying to show a very sharp peak down here. And this is pretty much what the effect that was expected to be seen. Prior to this, they could not see the changes that were occurring. The blue wave with enhanced calculations, I'm just showing you the data from the first step from the premix with this big shoulder, and then the final after the milling time was completed. Over here, one of the things, if you have a Micrtotrac, these notes can be really valuable, and you'll notice that Tony put information in these notes. These notes are like a little word processor, and it follows every record that's saved will have any information located in this note section that will be saved as well. But you can see the differences in the particle size, and particularly if around the 70, 80 percentiles, you can see how the data has shifted down to the smaller sizes. Now we also have the third instrument, which is the tri-blue. And the tri-blue uses 3 405 nanometer lasers, and these are very highly advanced calculations. And again, this allows us to take the blue lasers and use the calculations over the entire range of the instrument. Okay, this takes us back to what we call a full shift invariant function, and I really don't have the time to go through that right now, but I can send you an original publication on this whole concept. And if you visit one of our seminars that we do across the country, I can go into more detail about that at that time. Now, one of the things that's important is to be able to have sensitivity across the entire particle size range of an instrument. And this is showing 4 glasses ranging from submicron all the way up to very large particles. And this is a mix of those 4 different glass particles. The nominal sizes are shown down here, and the actual sizes that we achieved are here. Some of this is sieve sizes, some is microscopy. Microscopy is a nice image analysis technique, but it doesn't have the capability to measure a few 100,000 particles. It would take a very, very, very long time to be able to do that. So these are nominal values. They're not certified by NIST. But you can even see here, as we go down these sizes, this is peak summary data that's calculated by the Micrtotrac. It shows the 4 peaks and the various sizes that are present. Now, the nice thing about this is that if you have large particles and you're worried about those nice spherical particles fracturing in any way, you will have the sensitivity to see that fraction, those fracturing events, and maintain control over the handling of the material or any other part of the process that can bring about the fracturing of those particles. On the other hand, if you're trying to make glass that's very, very small, down in this region here, which is on the order of, I'm going to say half micron, then if the sizes are getting too large as you go through your process of making this, then you'll know when to stop the process and avoid making these larger particles, because if this is the material that's desirable to be made, then there would have to be another step in the process to remove any of these large particles that might develop. Now, one of the things that all of us in this business love to do is show you NIST polymers, and this slide shows just a few of those. I could show you a slide of about 20 different sizes, but it's kind of a confusing slide, so I decided to pick out just a few of them. And this is demonstrating the capability from the nano region to the submicron region. Now, according to ISO, just as an aside, ISO has a definition for nano-sized particles, and they are particles that are all from 100 nanometers down. Okay, the submicron region is from 100 nanometers up to 1 micron. So, measuring 28 nanometer, and again, this is certified diameters by NIST procedures. This is purchased material. This is 28 nanometers, 110 nanometers, and 220 nanometers. And this is on the other side. Over here, we were talking about particles going up in size. Now we're talking about particles going down in size. And this is the 50th percentile for that material, the 50th percentile for the 110, and the 50th percentile for the 220. Unfortunately, this is off by about 0.5% for the 110 nanometer. But I think that is just a very small difference when you consider the 28 nanometers and the others are identical to what NIST is providing for that data. Now, the importance of this is that if you're making a supermicron emulsion, which would be down in this size here, then if this emulsion is breaking, and when emulsions break, they tend to have, depending on whether it's an oil and water or water and oil emulsion, when they break, they tend to have the secondary phase will come together, such as oil and water. Then the oil droplets start to coalesce and form larger particles. And with this, with the design that we have in the tri-blue, you would be able to see those particles developing. This would be an indication that that emulsion is unstable. The other thing is, if you're trying to do emulsion polymerization, and those reactions have to be controlled fairly critically. If the emulsion polymerization isn't quenched or stopped soon enough, then you can develop these larger particles. So this would give you very good control over that, and while someone is monitoring the process and the particle size development for particles up in this larger region. So it gives good control over emulsion polymerization. The tri-blue, as I mentioned, it's always nice to look at nice spherical particles, but again, they tend to represent only a few percent of the materials that are measured for particle size. So the tri-blue has, this is some data on non-spherical particles, and the way we tested this was to look at dynamic light scattering. Now, dynamic light scattering follows first principles, which means that we're following the closest form of light scattering that can be achieved. And in Micrtotrac, we use a complete iterative deconvolution routine, which means that the algorithm is testing itself to make sure it's doing its own job. It's kind of like when if you're in class, you take a test, and the teacher passes it back to you and asks you to grade it yourself. I know that's kind of fraught with difficulties, but it does happen. But there is no curve fitting in the Nanotrac, and we do a full iterative deconvolution routine. Not all dynamic light scattering instruments do that, but we do it because we're looking for anything that can be involved with the distribution. The tri-blue uses an advanced iterative deconvolution, and it provides for the best possible calculations of resolution, sensitivity, and repeatability. That all goes back to the Fourier optics, the use of lasers, etc. This is titanium dioxide. And as I was mentioning, comparing the blue wave data to the Nanotrac at first principles gives us a good idea of how well the tri-blue performs. And notice that the size range here starts at 10 nanometers up to 100 nanometers up to 1,000 nanometers or 1 micron. And this is an overlay of tri-blue data and Nanotrac wave data, and you can see that the distributions are virtually identical. I have to thank Dr. Trainer for providing me with this data, and he was able to overlay tri-blue and Nanotrac wave data. And what we're seeing here are barium titanate samples, and there are actually 4 of them in here. 2 of them are just a little bit different down here on the fine end. And this is showing that the tri-blue is picking up a slight difference because it does have that capability of measuring down to 53 nanometers. Actually, it will go down to 10 nanometers down at this region here. But I've already shown you that there is performance down this region. but this is an irregularly shaped particle, and you can see that there are some slight differences between the two materials, sample A and sample B, which the customer was expecting. Over here on the right-hand side, we have titanium dioxide, and this is the big component that provides for white paint and other colors and pigments are added typically to a titanium dioxide suspension in the paint can to achieve the colors that are desired. And we have 3 samples of titanium dioxide here. And again, you can see how the instrument responds and picks up these particles going all the way down to about 35, 37 nanometers. And it clearly distinguishes between the 3 different materials. But at the same time, the Nanotrac data and the wave data are virtually identical. So we're actually able to get diffraction instruments going back to first principles of dynamic light scattering instruments. And I've heard comments when anyone is comparing any diffraction instrument on the marketplace to dynamic light scattering that the agreement is not the same. And this is because the technologies are different, the mathematics are different, and that's the reason why we went to a tri-blue system where we could use the best mathematics, the most powerful mathematics, to look at that fingerprint of the signals to give the best possible calculations.
Thank you for checking out this on-demand presentation. If you are interested in sending samples for complementary analysis or scheduling an on-site demo, please do not hesitate to send an email to jason.noga@microtrac.com. And for further information about our entire suite of particle analysis solutions, please feel free to check out microtrac.com.